Okay, welcome back. 6.5 is a method for solving a particular form of differential equation. It's the first order linear. And it's a clever method. We want to take a look at first order differential equation. Okay, first you want to identify the form, and there's a standard form upon which we sort of define the process that we use to solve the differential equation. So the standard form, what does that look like? It'll look like this: dy with respect to dx plus some function p of x times y equals some other function of x. Okay, so there it is. How do I solve this? Well, you're going to use what's called the integrating factor. And the integrating factor we call mu is equal to e to the integral of p of x dx. Okay, so in the book they give you kind of the formula for the solution. I really don't want you to memorize that. I want you to learn how to do the process. Okay, so let's go ahead and take a look at how this thing works first, and then maybe we'll turn around and work through some more of them. Okay, so here is first order. It's not separable. Okay, so sometimes these first order will be separable, and you can kind of just finagle the answer the old-fashioned way and backdoor it. But this guy is not going to be separable. You're not going to be able to get away with that. So how do I do it? Well, I'm going to want to find the integrating factor. And, well, maybe one problem you may have forgotten already. Y prime is equivalent to dy over dx. Okay, so if you really want to match up the form, you can rewrite y prime as dy over dx. It's not necessary. And then plus some function of x times y. Here it's not clear, but the function is just 1. Okay, so 1 times y. On the other side, q of x is e to the x. Okay. So this thing becomes your p of x. And then this thing is your q of x. Okay. We want to, once we get into this form, we want to form the integrating factor thing. Okay, so mu will equal e to the integral of 1 dx. Okay, and when we do this, we don't care about the constants, the plus c or any of that jazz. We just don't overthink it. We just want something simple. It's a tool that gets the job done. Okay, so the integral of 1 is just x. And then this thing is our integrating factor. So form this, then secondly, you're going to multiply through the original equation by e to the x, or when the standard form, okay? So sometimes the original equation is not in standard form. You need to be in standard form to do this. Okay, so multiply through by e to the x. I'll have e to the x, just for the sake of sanity, I'll write y prime. And then plus e to the x times y. And on the right-hand side, I'll have e to the x times e to the x. Okay. This side is really the derivative of e to the x times y, implicitly. Okay. So let me just show you that. Note the derivative with respect to x of e to the x times y is equal to, well, leave e to the x alone and take the derivative of y. So the derivative of y with respect to x is 1 times y prime. So you always tack on the y prime. And then plus take the derivative of e to the x, which is e to the x, times y. Okay, so this left-hand side, the way we've, you know, they did that on purpose. They made this integrating factor such that the left-hand side can be rewritten as the derivative of a product. Okay? You can replace the right-hand side with this thing. It's the reverse of the product rule. Okay, so this left-hand side is a derivative with respect to x of basically mu e to the x times y. Okay, on the right-hand side, e to the x times e to the x, you add the exponents. So it'd be e to the x plus x, which is 2x. And then we just integrate both sides with respect to x. Okay? On the left-hand side, the integral and the derivative are kind of like inverses of each other. They'll cancel each other out. Okay? On the right-hand side, then we have just the integral of 2 to the x dx, which we can do. So the left-hand side will turn into e to the x times y. And then the right-hand side, if you do a u sub real quick, you'll see that you have a 1/2 popping out. U is 2x, du is 2 dx. So that tells me dx must be equal to du over 2. So I could rewrite that integral as the integral of e to the u times, instead of dx, I write du over 2. So there's that constant of 1/2 that gets pulled out. And then the integral of e to the u is just e to the u, right? So I get e to the x, y equals 1/2 e to the u. And then if you back substituted, that's 2x. And then we can include an integration constant. Okay, ideally we want an explicit solution, so I'll divide both sides by e to the x. In doing so, I get y equals 1 all over so how can I explain this? E to the 2x all over 2e to the x plus c all over e to the x. And then right here, you could subtract the exponents, the quotient rule for exponents. It'll be e to the 2x minus x, which will just be e to the x. Okay, so you'd end up with e to the x all over 2. And then plus c all over e to the x. Okay, the constant of integration will not absorb this variable. Okay, it'll only absorb other constants. So at the end of the day, you end up with this expression as your general solution. Okay, so anyways, the idea is to use the integrating factor to set up this collapse. And what it is the reverse of doing the product rule. Okay, so when you do the product rule, the derivative of this will be this sum. Okay, and it's always going to work that way. This product will be mu times y, and then when you integrate, you're just going to have mu times y. And in the book, they'll give you a formula, but I want you to be able to do this process by hand. Okay. Okay, so let's try another one. This is now example 2. And we have xy prime minus 2y equals x squared. Okay, so the first thing to note is that this guy is not in our nice standard form. Right? So our standard form sitting right here, there is not an x in front of y prime in our standard form. So we need to divide everything by x. Okay, so that would be my first step. Y prime minus 2y all over x, or let's write 2 over x times y, because then it'll be in the standard. Whoops, that should be 2 over y. Oh, jeez. I'll rewrite that. Divide through by x, you get y prime minus 2 all over x times y equals x squared over x is just x. So if you write it like this, you can see the integrating factor is going to be e to the integral of negative 2 over x. So you have to also bring over that negative. Because the standard form has a plus in here. So when it's negative, the p of x is going to be all of this business. Okay, you have to include that negative portion. Okay, so let's go ahead and integrate that thing. We'll have e to the negative 2 times the integral of dx over x. This is equal to e to the negative 2 ln of x. And we don't worry about the absolute value, the plus c. No, don't do it. At this point, I can rewrite it. So do not leave it like this. You can simplify this. It's e to kind of an ln. And for you to simplify, you need the e and the ln to quote unquote touch, right? I need to bring this -2 into the guts of the ln. So it would be e to the ln of x to the -2. And then I can simplify. And then I can say, all right, these guys are inverse functions. They cancel each other out. We're just left with e to the -2. In other words, 1 all over x squared. Okay, once I get that, I'll take this character and multiply through this equation by this, and you'll end up with, sorry, you want to work with this equation, the standard form equation. It's this guy that I multiply mu by. So multiply, not this, okay, not the original, it has to be the standard form. Okay, so in that case, I got y prime all over x squared minus 2 all over x cubed times y equals x all over x squared, which is 1 all over x. The left-hand side will automatically collapse into the derivative with respect to x of mu, which is 1 over x squared, times y. And it's automatic. It'll always work that way. If you're not sure, you can check by taking the derivative implicitly. Okay, so note the derivative with respect to x of 1 over x squared is x to the -2, and then times y. Okay. So here, the derivative of y is y prime, so you end up with y prime times x to the -2, and then plus the derivative of x to the -2 will be -2x to the -3, and then times y. And then you see this thing is exactly the same as the left-hand side here. So it must be the case that you can collapse this expression into this expression. Okay, then you can integrate both sides with respect to x. On the left-hand side, the integral and the derivatives cancel. You get y over x squared. On the right-hand side, you get the ln of the absolute value of x plus c, and then multiply through by x squared. So you get y is x squared ln absolute value of x plus x squared times c. And again, the constant of integration will not absorb variables, okay? Only other constants. Okay, so that's sort of the game here for these kind of first-order linear differential equations. Let's take a look at an application then. In particular, we want to look at the tank problems. Okay, so you'll see these sort of on steroids later on in differential equations. You'll have multiple tanks being filled, but the picture here is some outlet pipe sending a mixture of liquid into some huge container, some tank. Okay, and then on the tank there's another outlet pipe, and it is dumping stuff out at some other rate. Okay. Okay, so if you have this scenario, you can show that the differential equation is the following: that the rate of change of the concentration with respect to time is equal to Q1 R1, and I'll define these variables here in a second, minus R sub 2 times Q all over V sub 0 plus R sub 1 minus R sub 2 times T. Okay, it's a bit complicated. It's really not. Where are all these Q1, Q2s, etc.? Well, the Q1 is the number of pounds of concentrate per gallon. So you could say it's basically like salt, if you wish. So Q1, we'll say, is the pounds of salt per gallon. Okay, and then we'll say R1 is the gallons of the saltwater solution that's going into the tank per whatever unit of time. We'll say minute. Gallons of salt water per unit of time, we'll say just minutes. Okay. Then inside the tank, there's going to be an equation Q of T that tells you how much salt, or how much salt is in the solution for a given time T. So this is amount of salt in the salt water at time T. And at time T sub 0, so at time 0, we'll have V sub 0 is going to be the gallons, the amount of salt water, gallons of salt water. And then Q sub 0 will be the amount of salt in there originally, or pounds of salt. Okay, and then the output we're going to put in terms are only given and will be R2, and that'll be the gallons of salt water coming out per minute. Okay, so we want to produce a differential equation for this scenario. And the book is telling you it's basically this. So can we figure out what the heck this thing is? And yes, we can. It's very simply, it's just going to be the amount of salt coming in minus the amount of salt going out. I believe. So the rate of salt going in, so the units are usually kind of the big key to figuring this out. This should be pounds per minute, and likewise this should be in pounds per minute. Okay. Right. So first, this guy Q1 QR is what we're after. So we'll say the amount of salt, the rate of salt going in. Well, what does that equal? Well, you can go back to this picture here, and what we want the units to be kind of dictate how we want to create this expression for the amount going in. So note, if you just multiply this Q1 times R1, what are the units? You're going to get salt in pounds per minute. And that's exactly what we want. Okay, so the rate of salt going in is just going to be Q1 times R1. Okay, and that will be in pounds per minute when all is said and done. Then the rate of salt going out is kind of the same thing. Okay. So we're given R sub 2, so you know it's going to be R sub 2 times this pounds of salt per gallon. So it's, maybe we can even include the units this time. So R2 is what? It's gallons of salt per minute, gallons of salt water per minute. And then we want to multiply it by some sort of expression that's given in terms of pounds per gallon, right? And I need a way of figuring out then essentially how much salt is in the salt water. So how do I figure that out? Well, it's a ratio of the amount of salt in the tank at given time t, which is just big Q of t right here, all over the amount of water in the tank at any given time t. So to figure out the amount of water or the amount of salt water in the tank, it's just the difference between the stuff coming in and the stuff coming out per unit of time. Okay, so of course you start at V sub 0, the amount of salt water you have at a given time, and then you're adding in basically a slope of R1 minus the R2, the stuff going out, times t. Okay? And so at any given time t, this is the expression you'll have. You can also create this equation just using points, right? So you know at time 0 you have v sub 0 in there, and then at time 1 you'll have r sub 1 minus r sub 2 gallons in there, because you're having r sub 1 gallons come in and then r sub 2 gallons go out. But it should be v sub 0 plus that, right? So it would be v sub 0 plus the difference between the amount coming in and the amount going out. And then if you just plug that into your equation of a line, so it would be v, the amount of salt water in the tank at time t, minus v sub whatever, 1 equals m times, I guess, q, minus q sub, let's say, 1. This should sort of get the job done, I believe. So the slope, and I think I butchered this. Sorry about that. The formula will be v minus v sub 0 times equals m times t minus 0. Sorry. A lot of variables floating about. So anyways, I have v minus, I guess, whatever point v I want. I need the slope regardless. So the slope will be this minus this. So it would be v sub 0 plus r1 minus r2 minus v sub 0 all over 1 minus 0. So the slope is just going to be r1 minus r2, which is what I said. The slope of this equation is that. And then to figure out the equation, I'm going to plug this point into the formula. So v minus v sub 0 equals the slope, r1 minus r2 times t minus 0, or it would be t minus t sub 1 up here. Okay. And then plugging in, I guess there's no plugging in the do, it's just you're going to get your formula. V is equal to r1 minus r2 times t plus the v sub 0 from the other side, which is essentially what I have down here. So what I'm saying is that you don't have to feel it out. You can literally use your methods from algebra to produce a formula for that denominator, which describes the amount of gallons of salt water in your tank at time t. Okay. So anyways, once you get this material, you got it. It's the change in rate of the salt in the tank is just the difference between the amount of salt coming in and the amount of salt going out. Okay, so it's this minus this, which is the original formula from back here. So hopefully that wasn't too all over the place, but there it is. So I'll come to class and I'll make that a little cleaner and hopefully more understandable. Okay, so we'll just leave it at that today. All right, thanks.